Hey guys, I'm Pranav, and today I want to give you a brief overview of the TCP IP suite. The TCP IP suite is really important, and what it does is it serves as the foundation of the modern internet that we use today. So to start it off, let's talk about the very basics, IP. What is IP? IP stands for Internet Protocol, and it works as the basis for communicating information between computers. If you wanted to call up one of your friends and tell them about your day, what's the first thing you're going to need? Well, obviously the first thing you need is their phone number so that your telecom company knows who to route you to. IP serves as the equivalent of phone numbers for computers. When I punch in google.com into my web browser, it gets resolved into an IP address. This IP address gives us which web server we want to request the web page from. This is the core aspect of what allows controlled internet communication. There are two versions of IP that are commonly used today, IPv4 and IPv6. So I'm going to read off some numbers here. IPv4 addresses are 32-bit integers, and there's 3.7 billion available IP addresses for general use, while the other 600 million are reserved for special purposes, whereas IPv6 addresses are 128-bit integers, and there's a lot of them. That number is 34 unidecillion. It looks like that. As more and more devices are connected to the internet and require IP addresses, we slowly start running out of IPv4 addresses. However, IPv6 allows for a lot more devices to be on the internet, and we're probably not going to run out anytime soon. So now let's move on from IP to ICMP. ICMP stands for Internet Control Message Protocol, and it's used to relay problems in the transmission of packets from one person to another. It's typically not used to exchange data between systems. The main use is diagnostic and control purposes. A good analogy of ICMP is if you ever try to call back a spam caller who's spoofing the number, you might get this annoying message.
Your call cannot be completed as dialed.
This is similar to ICMP. If I try to make a connection with an IP address that's not in use or is not listening, then I might get an ICMP network unreachable error back. There are use cases for ICMP, however, such as traceroute and ping. Ping is a term you're probably familiar with. It's used to test the connection between servers and also return the time it takes for a packet to be sent and received. Traceroute is quite different. It takes advantage of ICMP error messages to find the number of hops a packet takes from router to router to get to its final destination. Now that we've covered IP and ICMP, let's move on to TCP and UDP. TCP and UDP exist as protocols that sit on top of IP that allow for two very different types of communication between hosts. While IP instructs where the data should go, TCP and UDP dictate how they should go. First, let's talk about TCP. TCP stands for Transmission Control Protocol, control being the key word there. It was developed with one purpose in mind, reliability in data transmission between two hosts. On television and movies, you've probably seen people talk over radio using keywords like Roger and over and out. This is used to communicate acknowledgement or the end of a communication. These procedure words add structure to the conversation and allow both users to know that their information was translated and know when the conversation is over. And it works pretty well. Well, except in some cases.
Roger. Huh?
LA departure frequency 123.9er.
Roger. Huh? Request vector. Over. What?
TCP takes a lot of inspiration from radio telephony procedure. The core goals of these transmissions are reliability, ordering, and error checking. When a TCP connection is established, they do what's called a three-way handshake. The first thing that happens is the establishing client will send the destination client a request to establish a connection. The destination client will send an acknowledgement of that request and also a request to set up a connection from its direction. When the original client receives this acknowledgement and also this request, it'll send its own acknowledgement back to the destination, and thus the connection is established. The shorthand for this is SYN, SYNAC, ACK. SYN stands for synchronize and ACK stands for acknowledgement. Along with the SYN request, a sequence number is sent to synchronize the starting point of the data transmission. As the two clients send packets between each other, they iterate their sequence numbers from their starting point based on the size of the packet. This allows for the receiving side of the packets to know if a packet has been lost in transmission. It also allows for the order of the packets being sent to not matter, as the software on each side will just organize the packets after they've all been sent based on their sequence numbers. If we notice a packet's missing based on a sequence number not being there that we expect, then all we have to do is request that packet again from the original server. The header for TCP information looks like this, where all you have to do is fill in the bits corresponding with the correct information that's supposed to go there. As you can see, there's a lot of overhead here. There's a lot of extra data that we need to send to do all this bookkeeping. This is the main trade-off of requiring all this extra reliability. If a file sent over FTP isn't all there, then we have a corrupt file, and that file can probably not be used. It is very important in these cases for every bit of information to be sent and for each side to know that the information has been sent. On the other hand, however, UDP serves as the complete antithesis of TCP. UDP stands for User Datagram Protocol and is much simpler to understand. It's a connectionless protocol where its main tenets are efficiency and speed. It has a lot less of the overhead cost of TCP, but also loses all the reliability that we built up in TCP. It shoots out packet after packet at the recipient's IP, kind of like a fire hose, and it doesn't wait for a confirmation that a packet's been sent, it just keeps going. Because of the lack of bookkeeping, the UDP header is a lot smaller and looks like this. As you can see, it only contains the source port, destination port, message length, and checksum for error checking. As you can see, UDP is very efficient, and the header is only 8 bytes long. Compare this to TCP, where the header is 24 bytes long. Along with that, in TCP, you also have to send acknowledgements from back and forth, and there's a lot more bandwidth used to convey the same information. Common uses of UDP are Twitch streams, voice over IP, such as Skype, or real-time strategy games, such as any first-person shooter that you play online. When I'm playing a game like League of Legends or Call of Duty, I need to know what's happening right now so I can react properly. If I missed a frame or dropped a packet, I don't want to waste time asking for that packet again when it's already happened and is not that useful. In these situations, latency can seriously hinder the end-user experience. Common uses of UDP are Twitch streams, Skype, and real-time strategy. 1 minute. My mom's calling me. Hey Mom, how's it going? Good, good. Doing pretty well. How are you? Oh, no, tell me who you saw at the grocery store today. Mm-hmm. Yeah? Keep talking. She's gonna go on like this for quite a while. I don't think she cares if I'm actually listening. I'm gonna head out. Hope you guys learned something today. By the way, this reminds you of anything? That's a cut.